For a geometric sequence, we're going to be looking at number patterns, a list of numbers that have a pattern. So let's compare it to another type of sequence. An arithmetic could mean adding or adding a negative. I notice that each of these numbers is growing by 2. We are adding 2 every time to get to the next number in the sequence. We call that an arithmetic sequence. Basically, you are adding or subtracting a common difference to get to the next term. For geometric sequences, we're going to be looking at something that grows or maybe shrinks a little faster. Here we could say, well, 3 multiplied by 2 makes 6, and 6 multiplied by 2 makes 12. We are multiplying by a number. That would indicate a geometric sequence. There's some notation we want to talk about. So let's look at this table here. My first term is 4, my second term is 12, and so on. Notice that it's growing quite quickly. 4 times 3 makes 12. 12 times 3 makes 36. I can tell that my rate of multiplying is 3, or we sometimes refer to that as a ratio. Notice our definition over here is a sequence with a constant ratio or multiplier between the terms. So I know my rate is 3. One way we can note this is called recursive definition. Now, it's a little ridiculous. For example, if I asked you, what is the 12th term? You'd say, well, hold on a second. I'll just keep multiplying by 3 here 11 more times, and I'll get you the final answer. That's basically kind of how ridiculous or redundant a recursive formula is. Here are the 2 types of recursive notations. Subscript simply means these tiny little n's are written below. The n's can enlarge here and be written the same way. So notice we have the r here. In this case, our r would be 3. We're multiplying by 3 each time. A of n or a sub n always stays the same. I generally will write my recursive formulas with subscript, but we can practice both of them. That means if I want any nth term, for example, I told you the 12th term here. If I want the 12th term, I'm going to make that equal 3 times the 12th minus 1 term. That'd be the 11th term. A little crazy, you might say, that you have to get to the 11th term to find the 12th term. It's not super helpful, but it is one way to notate our recursive formula. Now, one thing we always need for a recursive formula is my starting value. So in this case, my table said to start at 1. So does this one, even though it's the big N written up high for our function notation, I would still write everything just like it says. So the main things you're filling in for recursive formulas are your rate and your starting value. The rest of it is simply copying that notation. So if we look at an example down here, notice these numbers are not that pretty. We can't maybe tell what we're multiplying by. That's when we kind of refer to that ratio again. I think of a ratio as a fraction. 3 doesn't feel like much of a fraction to me. But if I took my term before and divided a term here at 1.45 and divide by the term before, this will give me a ratio. Now, when I do that in this particular case, I get 1.18. It's important that you check every term to see if it's really multiplying by the same number. So I'm going to do this again just very quickly and see if 1.68 divided by its previous term to make a ratio is the same. It turns out that in this case, it is not. So since what this means is 1.22 was multiplied by 1.18 to get to 1.45. But it is not the same ratio. If I take 1.45, I have to multiply by 1.15 to get 1.68. So since these are not equal, this is not geometric. But let's look at one that is. If I take 0.75 and divide by negative 1.5, my ratio or my rate of multiplying is 2. Now just to check, I could take negative 0.375 and divide by 0.75, and I will get 2. And I guess it would be negative 2 here because it's a positive divided by a negative. It is always dividing, if you will, by a negative 2. So since those ratios are coming out the same, it is geometric. And my notation for recursive formula, I'm going to use subscript here. Would be a sub n equals negative, now notice it's getting smaller since those numbers are getting smaller, my negative 1/2, because I'm cutting those in half, times a sub n minus 1. And I want to make sure I indicate what number we started with, which is negative 1.5. This example's in your packet, and most of the time a geometric sequence isn't quite as yucky of a ratio. But it's the way to check if it's geometric in the first place is to divide the term ahead by the term behind it and see if they match. We do note that negative 1.5 divided by 2 or times a half would make 0.75. So our R value is the negative 1/2. And we wrote it in subscript notation here. So if we're looking for the 12th term of a sequence, let's say, for example, here 3 goes to 6, and we know we're doubling. We went back to a little nicer of a ratio here. If I wanted the 12th term or the 100th term, it's not very fun to say, well, hey, if you want term 100, you need to multiply by term 99 by 2. Nice. We don't know what term 99 is, and we don't care to figure that out the long way here. So an explicit definition allows you to find the term in the sequence without knowing the previous term. It's a very quick formula. And here are our two equations. So for this case, I will still write my a of n. That means any nth term that I want will be found by taking my first term, which is 3. We call this a of 1, or a sub 1. That's my first term in the sequence. Times my rate, my R value or ratio that we're multiplying by. In this case, it's 2. This would be my R value to the n minus 1. That's our explicit definition. Now that's function. You can write it as subscript. Again, not much changes besides the n goes from being a large size n to a small n. But just so you've seen both of them, there would be both of my explicit definitions for that sequence. Same thing here. Remember we were tripling on this table? My equation, I'm just going to write it in function explicit notation, would be a of n equals my first term, which is 4 in this case, times the rate of 3 to the n minus 1. Now, what's great about this is, if I wanted the 5th term, I could put my 5 in for the n. So that means if you want the 5th term, you can take 4 times 3 to the 5 minus 1, which is really 4 times 3 to the 4th, which is 4 times 81, and that does give us 324. It's much smoother than saying, hey, if you want the 5th term, you need to know the 4th term, or if you want the 100th term, you need to know the 99th term. We really like function notation because it's quick and gives us any term we want at any time. So I generally refer to my explicit function notation to find any nth term. Sometimes they write it a little weird on a piecewise function. This just means your first term. That's your start, your a of 1. This half here is what you're multiplying by. That would be your rate. So my explicit formula would be a of n equals my first term 5, that's only the first term, times my rate of 1/2 to the n minus 1. This notation here is my explicit formula. Remember, let's read it backwards. 3 would be my first term, that's what I start with. 2 would be my rate. They now want a recursive. That's not my favorite one, but if we would look back into the formula, that would say a of little n equals my rate of multiplying times a of little n, or subscript n minus 1, and my first term is 3. It's important that you can go from an explicit definition to a recursive definition or backwards. One note here, same idea as, remember, this notation can change. There's your same notation. You can check out your answer key, but remember, this tells you your first term and this tells you your rate.